Okay. Good morning once again to all. Uh, as we have discussed in the last lecture, what are the difficulties with the DFT? And for calculating DFT, we require how many number of multiplication, how many number of additions, that all we have understood. Hope you all have understood that part. Yes or no?
Yes, sir.
Okay. So today we will proceed with the further part again. So what exactly we have seen in the last lecture is, like, we have calculated the total number of real numbers required and the real multiplications and additions are required. Now this title, I think you all have written that. Have you taken this title?
Yes,
I
sir.
hope you all have noted this title. Diagram you have taken.
Yes, sir.
The complex addition conversion we are doing. Here we are just converting like two complex number into like how many number of real additions and the real real numbers, we are converting that part. So everyone has taken this diagram, or still anybody wish to take this? Hello,
Yes, sir.
is my screen is visible to all?
हाँ सर.
दिख रहा है ना सबको?
हाँ
What about others? Please give me the response.
Yes, sir, it is visible.
Okay, have you taken this diagram?
Yes, sir.
Okay, you just add one point there, like one complex addition is converted to two real additions. Just note that part. These are all the things we require for again MCQ part. Just note down. One complex addition is converted to two real addition. One complex addition is converted to two real additions. Next line you write. We know that for each value of k, for each value of k, for each value of k, there are n minus 1 complex addition. There are n minus 1 complex addition. Therefore, for each value of k, therefore, for each value of k, n minus 1 complex additions are, for each value of k, n minus 1 complex addition are converted to, can anybody tell me what will be the answer here? For each value of k, n minus 1 complex addition are converted to how many number of real addition?
N.
2 into n minus 1.
It is 2 into n minus 1 real addition, because for one complex addition we require two real numbers, right? So if we have like n minus 1 k value, then it will be 2 into n minus 1 real addition. You just write, which equals to 2 into n minus 1 real addition. 2 into n minus 1 real addition. Next line you write. We know that k varies from, we know that k varies from 0 to n minus 1, 0 to n minus 1, 0 to n minus 1 for computing DFT of x of n. For computing DFT of x of n, that is k takes n different values. that is K, that is capital K unit, right? K takes n different values, n different values. Hence, n minus 1 into n, hence n minus 1 into n complex additions are, so here you have to write n as a capital, n minus 1 into n, capital N, complex additions are converted to, so what is the answer here? What is the answer? Yes? Anybody? So what will be the answer? That is 2 into n minus 1 into n it is again. Okay, or simply which will be equals to, write it as 2n square minus 2n it is. So these many number of real additions we require. So these many number of real additions we require for computation of complete DFT again. Okay, so therefore just write that 2 into n minus 1 into n, which will be equals to 2n square minus 2n real additions. Therefore total real addition in computation of DFT, therefore total real addition in computation of DFT is equals to, total real addition in computation of DFT is equals to, anybody tell me the answer? Is equals to, कोई बताएंगे मुझे अभी? तो पहले हमें कितने रियल एडिशंस थे? 2n square real additions are there in first part, right? Plus in second part, what we have is, it is 2n square minus 2n as a real additions, which will be equals to, what we will get? We'll get it as 4n square minus 2n, or simply this will be equals to, write it as n into 4n minus 2. To compute a total number of DFT, we require n into 4n minus 2 as a real addition. To compute a total DFT, we require n into 4n minus 2 as a real addition. And total real multiplication in computation of DFT will be equals to, कोई बताएंगे मुझे? How many number of real multiplications are there? Yes? Am I audible?
Yes, sir.
How many number of real multiplications are there?
4n square.
Yes, it is 4n square. Okay, so this is what you need to remember. The total number of real addition required to perform a complete DFT is n into 4n minus 2, and a total number of real multiplication, right? You just please be concentrate on the words. Real multiplication required are 4n square. So this is, you may expect as a MCQ question again. The next title you just write. Functions required. Trigonometric functions required. So here, as we all know that, I have written the title, trigonometric functions.
Yes, sir.
Now, here we all know that Wn to the power kn. What we will write? Wn to the power kn can be written as, how it can be expanded? Anybody? क्या लिख सकते हैं हम इसको?
e raised to minus j pi n divided by
It is e raised to minus j 2 pi by n into kn.
kn.
So this is what we are expressing, right? Now suppose if I want to write this in cos function form, how do I write this? Cos and sine function, I'm going to write it as cos of 2 pi kn divided by n minus j sine of 2 pi kn divided by n. Okay. Now, here also we know that this function, we are writing it as wr to the power kn plus wi to the power kn. क्या मतलब है इसका? It is just simply combination of real number of twiddle factor and the imaginary number of twiddle factor. Now, if we compare that above equation with the below equation, then what we can write? Anybody? So WRN लिख सकते हैं यहाँ पे, as we know that this is WRN and WIN. Now what we can write? So we can write WRN to the power KN is equals to, क्या लिख सकता हूँ मैं? Real part, that is cos 2 pi kn divided by n. Okay, so what is this? This is what we are calling it as the real part of Wn to the power Wr to the power kn. Okay, Wn to the power kn we can write. So now, imaginary part, what I will write? What I will write as the imaginary part? Anybody?
Sine 2
Wi
pi
to the
kn
power
upon
n kn is equals to, what I can write? Yes,
minus sine 2 pi kn upon n.
it is minus sine 2 pi kn upon n. So this is for again the imaginary part of Wn to the power kn. This is for the imaginary part of Wn to the power kn. Now, so what is the value of n varies here? N is varying from what? 0 to n minus 1, and as well as k is also from varying from 0 to n minus 1. Okay. Are you getting this point?
Yes, sir.
Hello?
Yes, sir.
आ रहा है ना समझ में?
Yes, sir.
हाँ, sir.
Okay, you just write, we observe that n varies from, that is small n varies from 0 to n minus 1, 0 to n minus 1, and hence Wn to the power kn, and hence Wn to the power kn takes Wn to the power kn takes n different values, n, that is capital N different values, comma, similarly k varies from 0 to n minus 1. Similarly, k varies from 0 to n minus 1, 0 to n minus 1, and hence Wn to the power kn takes different n values. Wn to the power kn takes different n values, full stop. Hence, for simultaneous variation of k and n, Wn to the power kn takes n into n, that is capital N into n, just write it is n into n, is equals to n square different values, full stop. Therefore, number of trigonometric functions or values required for computation of DFT, can anyone tell me the answer now? Required for computation of DFT is equals to, anybody? What is the answer? Hello?
Yes, sir.
है क्या वहां पे कोई?
हाँ सर.
सुनाई दे रहा है ना?
हाँ.
So what is the answer now? So for one value, we are getting the two functions, right? यहाँ पे दो फंक्शन आ रहे हैं अभी, मतलब टोटल DFT कैलकुलेट करने के लिए I require like 2 into n square it is, because so this n is for small n, this n is for capital N, so total we require Wn square, and for this Wn we have the value as like cosine, sine, so the value for the total number of multipliers required are 2n square. Okay, so this is all about the number of trigonometric functions required for calculating the complete DFT. Hope you all have understood the
Yes, sir.
functions what we require. So let us write a summary here now. So summary, you just write. So this will helpful for you to understand again for the MCQ question. You just write a summary. Are you able to see my screen?
Yes, sir.
Yes, sir.
Summary like this will be helpful for you remembering again for this one for MCQ questions again, like baseline for computational complexity. The each DFT coefficient require n complex multiplication, n minus 1 complex addition, and all n point coefficient require n square complex multiplication, n into n minus 1 complex additions. Then next you write complexity in terms of real operations. Complexity in terms of real operations. 4n square real multiplication and 2n into n minus 1 real addition. Whether it is correct? 2n into 4n square minus 2n. Okay. 2n into n minus 1 real addition. Or
No, sir.
can I move further?
Yes, sir.
Okay. Now next we'll go to, before going to this classification part, we just write the next title as, the next title is properties of Twiddle factor. Just write next title as properties of Twiddle factor. We'll write it as properties of Twiddle factor. It is properties of Twiddle factor. You just write. Or simply we are writing it as Wn. We are calling it as a Twiddle factor here. Okay. And by use of this Twiddle factor property, we are reducing the complexity in this FFT algorithm. Okay. So you just add one line. Have you noted the title? Properties of Twiddle factor. In notation, we are using it as Wn. Just note, these properties are used by FFT algorithm. These properties are used by FFT algorithm. These properties are used by FFT algorithm to reduce the number of calculations. To reduce the number of calculations. Full stop. We know that the endpoint DFT of the sequence x of n. We know that the endpoint DFT of the sequence x of n is given by what is the formula here? The formula of DFT is x of k is equals to summation n equals to 0 to n minus 1 x of n wn to the power kn is the formula of DFT, as already we have seen this. Yes or no?
Yes.
Yes, sir.
Now You just note down this formula. X of k equals to n equals to 0 to n minus 1. X of n wn to the power kn. Here wn is called twiddle factor. Here the wn is called the twiddle factor and is defined as how we are defining this twiddle factor here, or wn. wn is equals to, as we all know that we are writing it like this, wn is equals to e power minus j 2 pi by n. We are defining it as twiddle factor, or the wn equals to e power minus j 2 pi by n, which exhibit the two properties. One is symmetrical property, and the second one is the periodicity property. Symmetrical property and the periodicity property. So with these two properties, this FFT will reduce the calculations again. Okay. So let us see one by one. So let us first understand what is this periodicity property, and then we will go back to this symmetry property. Let us write periodicity property first. You may expect this question as a theory question again in exam also. They will ask you to explain about the properties of twiddle factor. I think one of your question is there in assignment 2.
Yes, sir.
राइट तो वो कितने लोगों ने मुझे पूछा है कि सर ये नहीं है, हमने सॉल्व नहीं किया, बोल किसी जस्ट वन स्टूडेंट आस्क्ड मी ऑन दैट पार्ट. बाकी सब लोग उसको स्किप ही कर दिए विदाउट अंडरस्टैंडिंग. राइट, periodicity property of twiddle factor. Just write a statement. You write. Statement is what? The statement is wn to the power k plus n is equals to wn to the power k. So already we have seen the periodicity property of DFT. क्या था वहां पे? Can anyone tell me what is the periodicity property of DFT? Statement. कल ही आप लोगों ने टेस्ट लिखे. होप यू ऑल हैव प्रिपेयर्ड फॉर टेस्ट वेरी सिंसियरली. What is the statement of periodicity property of DFT?
If n is equal to x of n plus n, that is x of k is equal to x of k plus n.
Okay, so that is x of k equals to x of k plus n for the DFT case, and if it is for the IFT case, IDFT case, x of n plus n equals to x of n. Very good. Now let us write a proof for this. So proof of this we will write. So proof here. So how do we prove this? So here we know that wn is equals to, what is that the value we are having? E to the power minus j 2 pi by n. Okay. Now if I write this wn to the power k plus n is equals to, what I will write? It is e power minus j 2 pi by n into k plus n I will write first, or which will be equals to, simply I will write it as e power minus j 2 pi by n k into n again. Sorry, what I will write this can be written as e power minus j 2 pi n by n. Okay, so this n get cancels. What is the value of this? This value goes to 1. So this will be equals to what I will write. So it is again, which will be equals to, we will write it as e power minus j 2 pi n. So this complete part, what I can write? I can write it as wn or k as it is. So this is wn to the power k plus n equals to wn to the power K. So this is what a simple way of proof for this periodicity property. Are you getting my point?
Yes, sir.
Yes, sir.
Any difficulty here?
No, sir.
Yes, sir.
Okay. Can I move to the next part? So what is next one?
Yes, sir.
Second one we have as a symmetry property again. Okay. Second one we have as a symmetry property. That is, we'll write a symmetry property here. The second one. Symmetry property. So the statement for this is again symmetry property of Twiddle factor you can write, that is Wn. So for this we'll write the statement as, we are writing it as Wn to the power k plus n by 2 is equals to minus Wn to the power k. Wn to the power k plus n by 2 is equals to minus Wn to the power k. Now let us prove this. Proof we will write. Proof. So how do we write again? The same procedure we will use. Wn to the power, Wn equals to, simply I will write it as e power minus j 2 pi by n. Then I will write Wn to the power k plus n by 2 is equals to, can you tell me what I can write it is? I can write it as e power minus j 2 pi by n into k I will write into e power minus j 2 pi by n into n by 2. Barabar? Reading this point.
Yes, sir.
Now this n get cancels here. क्या बचता है यहाँ पे? So n will get cancels with this part. This 2 get cancel. Then e power minus j pi is equals to what? What is the value of this?
-1.
-1.
It is -1. और इसके लिए हम क्या लिख रहे हैं? What we are writing for this? This -1 is as it is. That is minus sign is as it is. For this I am writing it as simply Wn to the power k. Right. So this is what a proof of symmetry property. Understood?
Yes, sir.
So by using
Yes,
these
sir.
properties, we are just reducing the what we can call complexity or the calculations in the FFT algorithm. So now let's move to the next part. So any question here? Twiddle factor properties?
No, sir.
No, sir.
Can I move further?
Yes, sir.
So now let's move to our actual syllabus. So this is what all the basics required to understand this. Now let's write FFT classification. Just write the title as FFT classification. That is again fast Fourier transform classification. So here this is classified in two categories. One is based on a divide and conquer approach. It is classified as Radix 2 DIT FFT algorithm, Radix 2 DIF FFT algorithm. Just write down this classification. And based on the linear filtering operation, this is not there for your syllabus, so we will not look into this part. Based on the linear filtering method, it is classified as Godgel algorithm. Based on a linear filtering method, it is classified as Godgel algorithm. Right? So this is what the FFT classification. Have you noted the classification?
Yes, sir.
So first we are based on the divide and conquer approach, we are classifying FFT as radix 2 DIT. DIT stands for decimation in time, FFT algorithm, and radix 2 DIF, decimation in frequency, FFT algorithm. And next one is based on the linear filtering operation, it is classified as a Gorgel algorithm, right? So this is very important for the calculations again. Now, before going to start with this understanding the classification, now first let us understand how the complexities are going to be reduced. We just write the title as computational complexity. Computational complexity compared to direct computations. Just write the title as computational complexity compared to direct computations. Compared to direct computations. Compared to direct computations. Now take this diagram, or before that you just add one line. Have you noted the title?
Yes,
sir. Yes, sir.
Just write one line. Now let us see how the FFT algorithm. Now let us see how the FFT algorithm reduces number of computations. Let us see how the FFT algorithm reduces number of computations. Reduces number of computations. Full stop. The computation involved. The computations involved in the butterfly operation. The computations involved in the butterfly operation as shown in figure. As shown in figure. Just draw this diagram. Or hello.
Yes, sir.
wait, sir. Done, sir.
Okay. So now what you are understanding with this diagram? So here this small a and small b are acting like a input, right? So then here the capital A is the output we are writing. So while I am writing the capital A, which will be equals to this complete A plus, I'm just coming to this side, B multiplied with Wn to the power K लिखो यहाँ पे, right? We are having the habit of writing the K. Instead of R, you just write it as a K. Wn to the power K into B. This is just a notation change, right? So this complete operation, what we are calling is, we are calling it as a one complex addition. So this is like the output we are getting it as a one complex addition. Now, if I want to write the output B, what I am writing? This complete A is subtracted with the value of B, which is multiplied with W into the power K. So I'm writing it as A minus W into the power K into B. So this butterfly diagram is very important in the calculation of FFT part. Okay. Have you understood this diagram? क्या कर रहे हैं हम यहाँ पे? Yes or no?
Yes, sir.
Yes, sir.
So now you just write one line. From figure, we can say that. From figure, we can say that the butterfly operation. From figure, we can say that the butterfly operation requires two complex addition and one complex multiplication. Requires two complex addition, मतलब ये पहला वाला एक और ये वाला एक. So they two complex addition and one complex multiplication. And one complex multiplication. Now, to understand the number of butterfly operations required, let us consider n is equals to 2 to the power v. Let us consider n is equals to 2 to the power v. Where, what is this v here? Where, you just write, where v is the stages of decimation, where v is the stages of decimation, you just write stages of decimation, and capital N is, what is n here? What is n? And you remembering this equation is very important. V is the number of stages and capital N is the number of DFT points. The number of DFT points. Now, suppose if we have n equals to 8, suppose if we have n equals to 8, then what we will write? So 8 is equals to 2 to the power v, right? Or this equals to, simply we will write it as v is equals to, what we can write? Log to the base 2 n, or simply log to the base 2, n value is 8, or this will be equals to log to the base 2, this 8 can be written as 2 to the power 3, or this is equals to, simply we will write it as 3 log to the base 2 and 2. This is equals to, what is the answer?
3.
3.
3.
The value of v is equals to, we require it as a 3. Means if you want to calculate this 8-point DFT, we require how many number of stages? How many number of stages you require? 3 stages you require. Are you getting my point? Have you understood how I have calculated this v value?
Yes, sir.
Hello?
Yes, sir.
Are you getting this point or not?
Yes, sir.
Now, if n is equals to 8, we require a number of stages are 3. So, therefore, we can write it as, therefore, just write, therefore, the total number of butterfly operations is equals to, the total number of butterfly operation is equals to, what you will write? The total number of butterfly operation is equals to, you need to remember this again, like n by 2 into v, or which is equals to, simply it is n by 2, v is equals to, we have the formula as log to the base 2 n. which will be equals to, so the number of butterflies required for 8-point calculation is, if n is 8, we are calculating based on this. So n is 8 means it is 8 by 2 into log to the base 2, this is 8 again, or else this will be equals to 4 into, what I will write? What is the value here? 3. So which will be equals to 12. So for 8-point DFT word calculation, you require the number of butterflies are 12 it is. Getting my point? This is for n equals to 8. Okay. Are you getting this point?
Yes, sir.
The total number of butterfly required for n equals to 8 is like 12. Just write one more line. Hence, number of addition and multiplication will be, hence, number of addition and multiplication will be, so the formula for this is again, just write, the complex multiplication is equals to, complex multiplication is equals to, we have a formula here. This is like n by 2 log to the base 2n as a formula. So which will be equals to, again for n equals to 8. So we have it is again for n equals to 8. So this can be done as again 8 by 2 log to the base 2 8, or which will be equals to simply again 4 into 3. So the total number of multiplications required are 12. The total number of multiplications required are 12 in this FFT algorithm again. Barabar?
Yes, sir.
Now if you look at into the DFT, the complex multiplication required for calculating 8-point DFT, कितने लगते हैं वहां पे? The number of complex multiplication required for calculating DFT using direct formula, क्या वैल्यू है वहां पे? Can anyone tell me? Number of multiplications required to complete DFT. Yes, anybody?
N square.
It is n square. So agar 8, if you take n equals to 8, then n square means it is how much? 64 time multiplication is required. अभी यहाँ पे कम हो गया आपकी multiplication. Getting my point?
Yes, sir.
Right? So here, this is the way how we have reduced the complexity in FFT diagram by that butterfly diagram. Using this, using butterfly diagram, we have reduced the multiplication numbers. यहाँ पे normal DFT के लिए आपको 64 times multiplication चाहिए, और यहाँ पे for this you require only 12 times the multiplication. So this is how the complexity is reduced in FFT algorithm. Understood? Next,
Yes.
you just write, and the complex addition required. तो एक बटरफ्लाई के लिए एक मल्टीप्लिकेशन था, तो उसके लिए आई रिटर्न इट एज like 1 into here, like 1 multiplied with n by 2 log to the base 2n. Right. Next line, right? And two additions are required for, one butterfly. Two additions are required for one butterfly. Therefore, the complex addition is equals to, complex addition is equals to, can anyone tell me what will be the formula here? 2 into n by 2 log to the base 2n. Okay, so which is equals to 2 into n का वैल्यू कितना आपका 8 है, so 8 by 2 into log to the base 2 into 8, or simply this is equals to 2 into 4 into 3. So which will be equals to how much? What is the number?
24.
It is 24 number of additions we require. In comparison with DFT, DFT का फॉर्मूला क्या है आपका?
n square minus n.
It is n square minus n. ठीक है, तो अगर n square minus n अगर आप करेंगे, so how much you require? Like 64 minus 1. So you require 63 times addition here. Okay, so in compared to the DFT, here we require only the 24 times addition. So this is how the complex additions are also be reduced with the help of this FFT algorithm. Understood why FFT is faster? Yes?
Yes, sir.
Now, let us take one small table here. Just take this table. Here we can understand the complete difference. Let me extend for another 2-3 minutes. Just take this table. Is it visible?
Yes, sir.
So with this you can understand, and this you may expect as like one like MCQ question will be there based on this table. So the number of points, direct computations, complex multiplication, complex addition. And if you are using like a DIT FFT, complex multiplication and complex addition, and improvement in processor speed for multiplication. Finished?
Yes, sir.
So let me read it once again, like if anybody is having confusion. The first column is number of points. I have taken like 8, 16, 10, 24. You can take any number. So I have splitted that in two columns, like direct computation. That means with the help of DFT and using FFT. In direct computation, we have like complex multiplication, we require n square multiplication, and complex addition, it is n square minus n. Sorry, last we have taken n square minus 1. That is not n square minus 1. It is n square minus n. And DIT FFT, we are taking the formula as complex multiplication. We have it is n by 2 log to the base 2n, or complex addition, we have the formula as simply n log to the base 2n. And here we are calculating the increment in processor speed with the help of this multiplication values. अगर आप एडिशन के लिए कैलकुलेट कर रहे हैं तो you have to use this formula in a dividing method, like divided like n square divided by n log to n if it is for the addition. Right. Now, if we are taking this as the value, like if we have the value as 8, then what we will write for direct computation? The answer goes to 64. Barabar. What about this part? N square minus n. We'll get it as
56.
how much?
56. 56.
बराबर क्या 56 बराबर है 64 minus
हाँ sir.
8. 64 minus 8. How much it is? 56. Barabar.
56.
Okay. Then next, n by 2 log to the base 10. We require 12. Then again it is 24 as we already calculated. Now if we substitute all these values here, like n square divided by n by 2 log to the base 2n. N square is how much? This 64 divided by 12. The value goes to how much? 5.3 times faster than the normal DFT again. Understood?
Yes sir.
Suppose if I take n square, n value as 16 it is. Let me write here it is n, capital N. Let's take that value, number of points n it is. If I take it as 16, then what will be n square? Is 256. Then number of additions, complex addition required, 240. To go to this part, like it will be 32. You calculate it afterwards. Then again it is 64. And then it will be like 8 times faster than the FFT again. This will be again like 8 times. Okay. Suppose if your n increases like 1024, then what's happening? इसका वैल्यू बता सकते हैं 1048576. Then this will be again it is 1047552. And here we will get the value as 5120. And here we will get the value as 10240. And this will be 20.8 times faster than this. So with this table, what you can understand? Anybody? What you are understanding with this? क्या समझ में आ रहा है इससे आपको? Yes? Hello?
FFT computations are faster than direct computation.
FFT computations are faster than the direct computation. Like suppose if I increase the n number, here the FFT values are going to be like computations are going to be reduced as compared to the direct DFT value. So that means if you look at into the speed of the processor here also, as the value of n is increasing, the FFT value like speed of the processor is also faster as compared to the DFT value. So this is how we can say that the FFT is much faster than the DFT. Clear?
Yes sir.
Hope you all have understood. Then we will stop it here. So tomorrow we will start with the further part again. Now you can mark your attendance. You can mark your attendance. We'll stop the session here.